In our previous lecture, you saw that there was a number of stars nearby that were not just a single star, but they were binary stars. Stars in which you had two stars that were together and they orbited one another. So two stars and they would be orbiting one another. Now, to the naked eye, it looks like one star because you don't have the resolution to see two stars, but in the telescope, you can see two stars. Now, sometimes they're too close together even for the telescope to see, but we can still figure out that there are two stars there. And so this is the idea of binary stars. And about half of the stars that form in binary systems. One of the most famous binary stars is actually, if you look in the Big Dipper, then the star right here that makes up the handle of the Dipper. Okay, it's that right where the crook of the handle is. Now in this picture it doesn't show very easily, but there's another little star that's actually two stars right there that with the naked eye you can see as two stars. And so this is the star Mizar as the bright star, and Alcor is the companion. And so Mizar is actually a binary star. The other star is Alcor. In to the naked eye, you can see the other star, and you can see Alcor, and to the but in the telescope, you see that Mizar itself is actually a binary star or a double star. Well, it turns out these double stars out there that you see, or the binaries, are very common. We have 61 Cygni, we have 16 Epsilon Lyrae, that's one that's up right near Vega this time of year. And in even binoculars, you can see that Epsilon Lyrae is a binary star. But in telescopes, each one of these stars turns out to also be a binary star. And so turns out to be a very interesting sort of quadruple star. Beta Cygni. This is another star. It's kind of one of my favorites because it's actually one of the first binary stars I looked at. Beta Cygni, also known as Albireo. And you notice these two stars are different colors. One's kind of bluish and one's kind of what looks like yellowish typically in the telescope, but it's really kind of an orange color. And so it's also a binary star. That means they're different spectral types. And they're not even different spectral types, but they're different luminosity classes, because the blue star should be brighter than the orange star unless the orange star is a giant star. Beta Monoceros, triple star system. In small telescope, you can see two stars, and a little bit bigger telescope, you see one of those stars is actually two stars. And so, again, multi-star system. At least half, if not the majority, should be if not, the majority of stars other than the sun, other than very tiny little stars, are part of multi-star systems. The sun is a little bit different in that it's one of these stars that's just a solo star. In fact, many stars, probably more than half of the stars that are the sun size, are part of binary systems. So there's an interesting thing that I want to point out, because sometimes you hear about this, and that is that several decades ago, astronomers were speculating that maybe there is a companion star to the sun out there that's too dim to see, and they actually named the thing. They called it Nemesis, and even though they never found it. And the idea was that Nemesis would be in this very elliptical orbit, which would pass close enough to the sun now and then to disrupt the orbit of comets and cause one of them to eventually crash into Earth, causing a mass extinction event. And so the idea came about because certain geologists thought that mass extinctions happened kind of periodically. Well, as we learned more and more about the geological history, we found out that those mass extinctions are not periodic, and they're not all due to things running into Earth. And so the idea kind of fell out of favor. We now have much more sensitive telescopes and infrared instruments that can see even the dimmest and coolest thing out there, and we don't see anything. So we now have pretty much decided that there is no Nemesis star out there. Though every once in a while you'll see something on the internet from somebody who doesn't know modern astronomy, and they read about this idea from decades ago and they think that it's still a viable idea, but it's not. There is no nemesis star. So when you're looking at binary stars, we got to label them something, so we call them A and B. If there's a trinary star, we'd call the third one C. And they're called A, B, C in order of brightness. The brightest one is A, the next brightest one is B. And so Sirius is a binary star, so we call it Sirius A and Sirius B. The secondary star, the way we explain where these things are is that we define something called a position angle. And so we imagine a line from the primary star, draw a line due north, and then we measure an angle clockwise from north, and that gives us the position angle. And then the separation is how far apart the two stars are. And so by measuring the angle and the separation and doing this repeatedly over time, we can measure the motion of the secondary star and the motion of the pair of stars. And so that turns out to be very important in terms of understanding how stars work. And so this is how we do it. Now, typically, separation is measured in arc seconds because there's not much of a angle between the two, and you don't really know what the distance is unless you can figure out the distance to the primary star. So for much of the early part of the 20th century, this was what a large number of professional astronomers did, was they measured binary stars, and it really helped to solidify our understanding of stellar processes. In recent years, a lot of professional astronomers have gone on and studied other things. Binary stars aren't nearly as exciting as they used to be, even though they're still important. And so there's fewer people that study binary stars, but still, when I was at this last online meeting of the American Astronomical Society, there were several sessions on just binary stars. So they are still studied. Over time, then you can measure the relative positions. This is the star Kruger 60. It's also BD plus 56 degrees 2783. And these are photographs that were taken over a period of a number of years. And you can see that the secondary star is moving around the primary there. And so this turns out to be a very important thing in terms of measuring masses of stars. So again, we have another one here. Now that star took decades to go around. This star, it takes months to go around, or years or so. So you can see over the span of much less time. It's 70 Ophiuchi. It was here in 1830. And then it took, all the way back to 1912 to about there. And so this is something that takes almost a century to go around. In fact, close to 88 years for one complete orbit. And so why do we care? Well, because as they're moving, it's really not just one star moving. This star is moving, but the other star is moving too. Newton's second law of motion, F equals ma, but Newton's third law of motion, for every force there's an equal and opposite force. So they really are both moving, and they're moving around the center of mass point. So as one star is moving, the other star is moving, and they're both orbiting around that center of mass point. Now, Isaac Newton reformulated Kepler's third law of motion. Kepler's third law of motion said that for planets going around the sun, there's a relationship between how far they are from the sun and how long it takes to go around. Newton added on the total mass times the period squared, measured in years, is the semi-major axis. So that means if you have an elliptical orbit, that's going to be half of that widest distance is the semi-major axis. You can think of it kind of like as the average distance. And that's the average distance measured in AU. And this total mass is solar masses. Okay. And so we just do algebra on that and find that the total mass